Welcome you all to this new lesson of circuit theory. Today we'll be discussing about some numericals on network theorems. So before starting our discussion, let me tell you what we discussed in last few classes. In last few classes, we discussed about very powerful network theorem tools such as superposition theorem, Thevenin's theorem, Norton theorem. Now, our purpose of studying all these theorems is to analyze an electric circuit. In which sense? In order to determine current through a particular branch or voltage across a particular branch. Now, we'll be solving today some numericals of applying all those theorems so as to get more clear understanding about the theorems. So let us start with some numericals. See here, an electric network is shown here, which is having two voltage sources, and all these sources are AC type. Now we are asked to find current through this R branch. We are asked to find current through this R branch. VS1 and VS2 are given. This is to be found. Let us, here it is not mentioned by which theorem we must move. So let us apply superposition theorem here to solve this network, to find current through R resistance. As the network consisting two sources, so superposition theorem easily can be applied. Now, this is the given circuit. We know as per first step of superposition theorem, consider each source separately. So let us consider this source for the first time. While considering one source, the other source, this VS2, this source has to be deactivated as no internal impedance is given here. So VS2 has been shorted while considering this source alone, VS1 alone. Now this is C1. Frequency of supply is 10 kilohertz. So the impedance offered by the capacitor C1 will be calculated by this formula. So this is impedance of C1. So impedance will be minus J 1.59. Okay. Now why minus J comes here? Actually XC1, if we consider magnitude only, then formula for XC1 will be 1 by 2 pi FC1. But if its angle is to be considered, then it should be 1 by J 2 pi FC1, as we discussed in class of superposition theorem. So 1 J will come here. That is why it will be minus J into 1.59 kilo ohm. Similarly C2 will be minus J 796 ohm. So while considering this source, what we are going to find? We are going to find current through this branch. So how the current should flow? Due to this source, a current will start flowing through this path. Current will flow through this. When current comes to this point, one current will be flowing through R resistor, another current will be flowing through C2 capacitor. So to find current I, say this is I dash. To find current I dash through R due to VS1 source, what we need to do? We need to apply current divider rule. So while applying current divider rule, let us assume this current is I1 dash. So this total current I1 dash will be divided into I dash, and say this is I2 dash. So total current will be divided into I dash and I2 dash. Now, So it is very clear to us, if we apply current divider rule to determine current through R, it is important for us to determine I1 dash first. So how to find I1 dash? How to find the total current? Total current will be total voltage Vs1 divided by total impedance of the circuit. So what is total impedance of the circuit? See, these two paths are in parallel. With this parallel combination, this C1 capacitor will be in series. So equivalent impedance of the circuit will be, this is in series with this parallel combination. So this parallel combination R and XC2's parallel combination will be RXC2 by R plus XC2. Here C2 will not be considered. XC2 will be considered because XC2 is impedance offered by the capacitor. Okay. So XC1 is minus J 1.59 kilo ohm, which could be written as 1.59 in polar form, 1.59 angle minus 90. So minus, for minus J, this is in rectangular form, for minus J, minus 90 will appear in the angle. So how this conversion takes place, that is already discussed in previous classes in calculation of AC quantities. So you may go through that if you have any confusion regarding this conversion. So this is XC1. Similarly, this is R and this is XC2. So by substituting all these values, we'll get Z equals to this. Now see here, after making this calculation, see, these are in polar form and we are going to add them. So as I told several times, quantities should not be added. Rather, I must say, quantities can never be added in rectangular polar form. To add two quantities in polar form, first what we need to do, we need to get the rectangular form of the quantities. That is why this is converted into rectangular form. This is also converted into rectangular form. So this is rectangular form of 1.59 angle minus 90. And this is rectangular form of 622 angle minus 51.5 degree. So finally we'll get this as Z. Now converting again it into polar form, we'll get Z equals to this. Now IS1, that is total current. This is IS1. Due to VS1 source will be total voltage VS1 divided by Z. Z is found in last slide as we discussed. So by making this division, we'll get IS1. Now once IS1 is found, this IR1, suppose this is IR1. This IR1 can be found using current divider rule. Now this IR1 will be IR1 equals to total current IS1 into, which one is opposite impedance? XC2. So XC2 is opposite impedance divided by sum of the impedances R minus JXC2. So finally you'll get this as IR1. So IR1 is found, which is flowing through R due to VS1 source acting alone. Same procedure will be following for VS2 source while it is acting alone. Now what will you do? We'll Consider this source and we will replace this one. So this one will be replaced by a short circuit. Clear? Same procedure will be following with VS2. So current will be flowing like this. Now in this case, current will be divided into R and C1. So these are in parallel combination. With this parallel combination, C2 is in series. So Z will be in this case XC2 plus RX1 RXC1 by R plus XC1. Now substituting all the values, we'll get Z equals to this. Clear? Now once Z is found, this ISC2, this IS2 could be found by equating IS2 equals to VS2 divided by this Z. So total current from source 2, that is IS2, will be equals to VS2 divided by Z, that is this. Now similarly IR2 will be IS2 multiplied by which one is opposite impedance now? This one, that is XC1 divided by R minus JXC1. So finally you will get IR2 equals to this. At last, in the last step of superposition theorem, what shall we do? See, we are going to find current through this branch due to both the sources. So considering VS1 source alone, we have got R1 equals to this. Considering VS2 source alone, we have got IR2 equals to this. Now IR1 and IR2 both have been converted into rectangular form so as to perform addition operation, because current through R due to both the sources will be algebraic sum of all the currents flowing through R due to each source alone. So due to each source, IR1 and IR2 will be flowing respectively. So total resultant current due to both the sources will be IR1 plus IR2. So this is the answer. So finally you have got total current flowing through R resistor due to both the sources acting together. Now let us solve another problem. See, here a problem related to Thevenin's theorem is given. Find VTH of the figure below. How to find VTH of the figure below? Here, this is RL. So RL is considered as load resistance. So what is first step of Thevenin's theorem? First step of Thevenin's theorem is to mark load, identify the load, mark load terminals. So load is identified as it is given by RL. Sometimes in question it may be given that find current through this branch. So the branch through which current is to be determined will be considered as load resistance. So here that is not given. Here RL is mentioned in the circuit. So this is our RL. So first we have identified the load. Load terminals are already marked in the question. Then what will you do? We'll remove the load. So after removal of load, the circuit will be looking like this. In between A and B, there was RL. Now after removal of load, this is RL. So what we need to find? we need to find VTH across this open circuited terminals. So how do we do that? See, this voltage source, this is Vs. Now this Vs voltage source is in parallel with XL, and also it is in parallel with this CR combination. Okay, so across this C, this is XC and this is R. Across this XC and R, that is capacitor and inductor, this Vs voltage will appear. Now XC and R are in series. So what shall we say? Voltage divider rule can be applied here to find voltage across R. Now the question is, why we need to find voltage across R? See, this R resistor is in parallel with this AB terminal. So voltage across R will be equals to VTH. So VTH equals to VR. Now VR could be found by using voltage divider rule. So total voltage Vs into resistance across which voltage is to be determined. So we are measuring voltage across R resistor. So R divided by sum of the impedances R minus JXC. Now R is 10 kilo ohm, that is 10 angle 0 degree. 10 kilo ohm, and XC is 10 kilo ohm. So minus J10. JXC will be J10. And VS is 5 angle 0. Now simple calculation is involved here. These two are, this is in which form? This is in rectangular form. But as we will be performing division operation here, so we have to convert 10 minus J10 into polar form. So we have converted into polar form. So conversion from rectangular to polar is already discussed. It's well known to everyone present out here. Now, after making this division, it is to be multiplied with 5 angle 0. Finally, you'll get this answer. Okay. So this is how you can calculate VTH for a specific network. Let us move to next problem. Okay. Here, we're asked to find ZTH or Zn. As we already discussed, determination of ZTH or Zn will be same procedure. So in Thevenin's equivalent circuit, which is termed as ZTH, in Norton's equivalent circuit, the same will be termed as Zn. So calculated value of ZTH and Zn will be same. So how to find Zn for the given circuit? Here this is RL. So first we have removed the load. We have removed the load and we'll look back into the network from open circuited load terminals. So while looking back into the network, that means, as I said, you are initially at point A, you want to reach at point B. So how can you reach? You may follow this path. Okay. When it comes to this point, you have two different paths. You may follow this path to reach at this point, or you may follow this path from this point. You may follow this path to reach at this point. So what can we conclude here? This path, and this path, blue and green paths are parallelly combined. Okay. So for this path, equivalent impedance will be R1 plus minus jXC1, and with this series combination, this should be in parallel. So R minus jXC1 is in parallel with XC2. So R1 R2, that is R minus jXC1 into R2 means here XC2 divided by sum of these three resistances. So this part gives us equivalent resistance of this network. Okay. With this equivalent network, this R2 is in series. That is why plus R2. Okay. So ZTH will be this. Now substitute all the values. You'll get your answer like this. Remember one point. While trying to find ZTH or RTH or ZN or RN, we have to deactivate all the sources. So here, see, the voltage source is deactivated by short circuit. If it is a current source, then it would have been replaced by an open circuit. Now let us move to next problem. Okay. Again, we are asked to find Zn first. For the same problem, we have to find In as well. Okay. So how to find Zn? This load will be removed. It is not shown here. This load will be removed. You'll have to look back into the network to find Zn, replacing the voltage source by a short circuit. So what will be Zn? Zn will be parallel combination of this is Zn. So I'm not going into details of this. In last problem, we solved the almost same problem. Here, let us try to find In. That is Norton's equivalent current. So how to find Rn? First, load is to be removed, then load is to be shorted. So load is removed and shorted. In is current flowing through this shorted path. So while finding Rn, you need to know what is I, because the main current will be divided into In and through resistor. So to find this total current I, we must know the total impedance of the circuit. So total impedance of the circuit current will be flowing like this. So total impedance will be parallel combination of these two. With this parallel combination, this XC1 will be in series. So XC1 plus R into XC2 by R plus XC2. So XC1 is 50 ohm. As always, XC will be, capacitor will be associated with minus J. So it will be 50 angle minus 90. Now why capacitor is associated with minus J? If you remember phasor diagram of voltage and current of a capacitor, or if you remember impedance triangle, this is R, this is axis of XC, which is in negative J axis, and this is axis of XL, which is in positive J axis. So whenever there is inductor, it would be associated with plus J. Whenever there is capacitor, it would be associated with minus J, if it is not mentioned in question. Okay. Now, so XC1 is 50 angle minus 90, R is 56 angle 0, R is 56 angle 0. R will have always, R is always in parallel to x-axis or reference axis, so it will have 0 degree phase angle all the time. So R will have 0 degree phase angle. Capacitor reactance offered by capacitor, that is capacitive reactance, XC will be associated with minus 90 or minus J, and XL, that is inductive reactance, will be associated with plus J or plus 90 degree angle. XC2 is 100 ohm, that is 100 angle minus 90, and R is 56, XC2 is minus J 100. Now see, while we are here, multiplication is involved between these two quantities. That is why XC2 is given in terms of polar form. As in the denominator, subtraction is to be performed, the XC2 is given in rectangular form. So you may represent XC or XL in polar form or rectangular form depending on the operation you need to perform. So finally you'll get, after making the conversions and simplification, you'll get Z equals to this. Now as Z equals to this, so what would be I? Current through this path, I will be Vs by this Z. So Z in polar form this, so Is equals to Vs by Z. So Is is found. Now In will be found by applying current divider rule. So In equals to opposite resistance is R, that is 56, R divided by R plus XC2 into total current I. Substituting the values, you will get this answer. So this is how you can solve AC networks as well along with DC networks by applying Thevenin's theorem, Norton's theorem, or superposition theorem. So the main important point here is, if a source, if an network is having multiple sources, then it is better to apply superposition theorem. If a circuit is with single source and different with a lot of complexity, then Thevenin's theorem will be applicable suitably. If the source is having voltage, if the source is of voltage source type, but if current source is given in the network, then Norton's theorem will be more suitable compared to Thevenin's theorem. So depending on the type of circuit, you may apply superposition, Norton, or Thevenin's theorem. So as of now, today I'm ending up here. In next class, we'll be discussing about some other parts of network analysis. In next class, we'll be discussing about maximum power transfer theorem. So what is maximum power transfer theorem? Why shall we study that? What's the proof associated with maximum power transfer theorem? How to solve electrical network using maximum power transfer theorem? That all we'll be discussing in next class. So thank you all for your presence. Meet you in next class. Thank you.